Jnanam paramam dheyam. Knowledge is supreme.
Group of these matrices which don't commute, they are in general called non-abelian groups. Okay. If you do a rotation about one axis, only one axis, will they commute or no? They will commute. So that is called abelian group. The group of matrices which you write about only one axis will be an abelian group. But if you have three axes, three independent, linearly independent axes, the rotation matrices in general don't commute. The reason for them not commuting is that the generators, which are angular momentum, they don't commute. Okay. So such is what you see naturally coming up here, even from the rotation matrices. So you redo the exercise which I did for R about x-axis with epsilon angle and R with by the same angle about y-axis, and keep terms up to order epsilon squared. Okay. Please redo this. If you keep terms up to order epsilon squared, you will see that you get commutator. This is nothing but it's a commutator of Jx, Jy. But you know that this right hand side was rotation about z axis by an angle epsilon squared minus identity. So try and write that out. If you do that, 1 minus I by h cross epsilon squared angle times Jz minus 1, they cancel. If you compare the epsilon squared terms, you get automatically that the commutator of Jx, Jy is non-zero and is exactly what you have been studying, giving you h cross times Jz. Okay. So the above equation gives us the familiar relation. Now comes this, the lowest angular momentum you can have is a non-trivial one. Spin 0 is a trivial one, right? Why is it a trivial one? It goes as if you don't see it, right? If you try to take a spin 0, you can write it as a 0 element 1 by 1 matrix. There is nothing non-trivial about it. Okay, you can't write numbers. If you write a 1 cross 1 matrix for a spin 0, you can't make it to be non-commuting. The only way you can satisfy this relation is that take Jx to be 0, Jy to be 0 and Jz to be 0 so that it satisfies trivial. So it's a trivial, spin 0 is a trivial representation. The next one is spin half, that is the first non-trivial representation. Okay. So for spin half, you can construct unitary operator. Spin half will have two states possible. J equal to half will have m equal to plus half and m equal to minus half. There are two states possible. You can denote J equal to half, m equal to half as 1, 0 and J equal to half, m equal to minus half as 0, 1. You can write Jx, Jy, Jz as 2 cross 2 matrices. We have done this in the Stern-Gerlach. I am just putting it from the group theory picture here. And you can have these set of 2 cross 2 unitary matrices and you can check those matrices which you did. Sigmas, the poly matrices were all traceless matrices, right? So we can take Jz to be half of h cross times sigma z, where sigma z is the poly matrix which is 1, 0, 0, minus 1. If you take exponential of I theta z Jz by h cross, this is the unitary operator for rotation about an angle theta z, z hat if you want to put it. Will this be determinant of u? What is it? This will be e to the power of I theta z by h cross trace of Jz. and they are all traceless matrices. The poly matrices are all traceless. Other factors doesn't really play a role. So e to the power of trace of jz is 0. So which implies determinant of u is plus 1. So this collection of these UR matrices will be called as S, U for unitary. The first non-trivial dimension of the vector space in which it plays a role is 2 dimension. So we write the notation as SU2. This 2 is for the first non-trivial angular momentum which we studied. So the lowest non-trivial J is spin half. We can construct 2 cross 2 unitary matrices with determinant 1, and this is what we call it as an SU2. Okay, I have not really written it here, but I have said it here. The set of unitary matrices form a group SU2 which represents rotations in quantum mechanics. Look at rotations in an abstract 4-dimensional space. Take x1, x2, x3 which are your x, y, z and add one more coordinate. You can still construct 4 cross 4 orthogonal matrices. Nobody prevents you from doing it with determinant plus 1. If you do that, then that collection of matrices you can call it as SO4. Should be a complete exhaustive set. And similar to what we were been talking about, any transformation or any symmetry transformation should be generated. Here SO4 can be generated by rotation about a plane. That's what I was telling, that earlier you had talked, if you are confined, if you are an ant and you are confined to be only on the plane, you say you are doing a rotation about a point through the center of the plane. When you make it 3 dimension, then you talk about rotation about an axis. When you go to 4 dimension, it's rotation about a plane, and so on. So it keeps going. So typically when you do a rotation, only 2 of the coordinates are getting mixed. So the coordinate xa and xp, they get mixed, and the generator can be formally written with those coordinates which gets mixed, rather than worrying about the remaining plane or. So this is a nice neat way of writing. In hydrogen atom, this is what I was telling. For completeness, I thought let me put in here. We have both angular momentum is conserved because it's a central force problem. You also know that the Runge-Lenz vector is conserved. This Runge-Lenz vector being conserved, you may not have a symmetry transformation to understand it. That's why sometimes we call this to be a dynamical symmetry. They may not have this physical geometrical symmetry like translation or rotations to understand them, but it's still conserved. So it's some kind of an abstract symmetry which is called dynamical symmetry. And you can compactly write your Runge-Lenz vector as if you are looking at a fictitious coordinate which is the 4th coordinate and 4th momentum, and rewrite your angular momentum Li. Here this I, this A and B denotes 1, 2, 3, 4, and the IJK will only denote 1, 2, 3. So I have put in here where this one is 4 and this one is I. So again there are 3 components here and 3 components here. So there will be 6 generators for the SO4 group, right? This is antisymmetric. How many independent possibilities are there here is 6. So 6 generators, using which you can start studying even the hydrogen atom problem as if it has a fictitious 4th coordinate. It has no meaning, but as mathematical problem you can solve them and see whether you can get the spectrum as proportional to energy spectrum proportional to -1/n squared. So I am not doing this. If anybody is interested, please go and look at Schiff, Symmetries in Quantum Mechanics, where he talks about this dynamical symmetry and works out the spectrum very nicely. Okay. Quantum mechanics does not distinguish whether you do only orbital angular momentum or you do spin angular momentum. SU2 can also be for the orbital angular momentum, but that's a higher dimensional representation of the same group. So just because you write 3 cross 3 matrices, you can still write unitary operators. Okay, so now that you got it, let me explain a bit. So what you can do is you can write your LZ as 1 0 0 0 0 0 0 0 -1. You can write a unitary operator for rotation theta z about z hat for spin 1 or for L equal to 1. Both are same. Spin 1 I mean j equal to 1. Here I mean L equal to. When I write an exponential of I theta z L z over h cross. Yeah. So I am not really separating what is S and what is L. J per se can be 1. How the S and L goes into that J, I am not worried. What I am worried is whether I can give a matrix. You have to write Lx and Ly. This I think is there in one of your tutorial sheet or assignment, right? You can also write a similar thing for Jx, Jy and Jz. You don't need to say what are the components of S and L. We'll come to it at some point. We will do the Klebs-Gordon. Right now when I say I give you in physical rotations, if I give you the orbital angular momentum, you can still construct unitary operator for it. But if I don't say it is orbital angular momentum, but it's a spin j, by that spin j, it can have a piece which is orbital angular momentum, it can have a piece which is spin angular momentum. Together it could be a 1, j equal to 1. So it doesn't mean that you are trying to say spin j equal to 1 is not SU2. Here when you write 3 cross 3 matrices for this, for spin 1, why do we call still a SU2? I was very careful when I said look at the lowest non-trivial dimension, right? But you can do it for spin j equal to 1. You can write a 3 cross 3 matrix, need not be polymatrix, right? J equal to 1 will have 3 states, that also you agree, right? But there is something more. You are only looking at rotations in that space. There are only 3 possible parameters. Okay, there are only 3 possible parameters and you have only 3 possible generators. Just because you exponentiate with 3 parameters and the j, which can be a 3 cross 3 or a 2 cross 2 or a n cross n, does not mean you go to SUN. We have seen from SO3 to SO4, you have seen, what have you seen? SO3 had only 3 generators and 3 angles. SO4 has what? The minimal non-trivial matrices which you can write is 4 cross 4 with 6 generators. So just because you write Jx, Jy, Jz as 2 cross 2 or a 3 cross 3 or a 4 cross 4 matrices doesn't mean you go to SUN. That's not right, because there are only 3 parameters and 3 generators. You are still doing rotation in an abstract space, and the matrix representation of the abstract space which satisfies the SU2 angular momentum algebra is strictly this. You are not going out of this. SO4 algebra and SO3, this is also similar to your SO3 algebra, right? SO3 algebra has Lx, Ly equal to IH cross Lz. But SO4 algebra is different. I can always write a set of rotations in 3 dimensions as a subset of set of rotations in 4 dimensions. Those will involve only these 3. But they will look like a 4 cross 4 matrix. Looking like a 4 cross 4 matrix doesn't mean it is SO4. It should be a complete set exhausting all possible generators. Okay. Writing a 3 cross 3 matrix for a spin 1, you cannot judge that it is SU3. You have to see how many parameters are involved, how many generators are involved. If I write that as e to the I theta dot j, where j could be 3 by 3 for spin 1, then I should know it is SU2. You have to only look at the first non-trivial lowest dimension and fix it. This is also an exercise for you. I don't even tell you about rotations. I just ask you to use this condition that R transpose equal to identity, determinant R equal to 1. Try to find the number of independent bases possible. In the case of SO3, in the case of SU2, and in the case of SO4. You can actually check and show that the number of independent bases or the generators will be 3 for SU2, 3 for SO3 and 6 for SO4. Sure, you would have done this. Number of orthogonal matrix entries when you write, symmetric matrix entries you write, you know how many non-zero entries are there, right? Antisymmetric matrix in 3 dimension has only the upper diagonal and the lower diagonal is negative of the upper diagonal. So there are only 3 entries. Similarly for unitary matrices where it is exponential of Hermitian, if you put hermiticity condition on a 2 cross 2 matrix, how many independent entries are there? If you put determinant to be equal to 1, how many will get reduced? Please check it independently. Okay, that will also clarify for you just by writing higher dimensional representation for SU2 does not mean you can call it as SU3 or SU4 and so on. Depends on how many parameters and how many generators. Okay, so for SU2 you can denote a vector as R dot sigma. Okay, this is one way of writing it. What is R dot sigma? It is nothing but Z minus Z. This is X plus IY or X minus IY and X plus IY, something like this. What does rotation do for you? A vector R goes to R prime, which is R times R. What does this do for the SU2 is that if you take U of theta, this is R of theta, R dot sigma, U of theta, U dagger, that will give you R prime dot sigma. So the analog of this equation in SO3 will be this, even in physical space. There's something now you can note that if you take the 2 signs here, okay, you can take U with an identity, U of theta and minus of U of theta will both give you the same equation, right? Because there are 2 U dagger is there. So the identity matrix here can be either represented by identity or minus identity. Huh? It's a homomorphism. It's a 2 to 1 map. Okay. So this tells you that it is not 1 to 1. So if you write a set of R's, R1, R2, R3, you can have a U1 minus U1, both of them correspond to this. Okay. So that is the subtlety. Algebra is the same. But if you are looking at the physical rotation which involves integral angular momentum, those matrices can be made isomorphic to SO3. But if you are looking at half-odd integral, then you have this way of looking at it. And you can see that there is a 2 to 1 map. So that's why we say that SU2 is homomorphic to even though the algebra is the same. There are still 3 parameters and 3 generators. Just because it is 3 parameters and 3 generators, you should not come to the conclusion that you are studying. SU2 is a necessity if you want to look at a space of both integral and half-odd integral. But you can live with SO3 if you are only looking at a space of integral, which is what happens in your hydrogen atom problem with only orbital angular momentum. There is no half-odd integral coming up. The Stern-Gerlach experiment is the one which forced us to look at spin half. Why only spin half? The algebra which we did using Schwinger oscillator method told you that you can have half-odd integral. And we tried to conclude that J could be integral or half-odd integral. If you want to have everything as a universal J which is integral and half-odd integral, you have to work with SU2. So some of these are practice exercises for you which I want you to do. Okay. What will this matrix element be? J minus. J plus is Hermitian conjugate of J minus. So this matrix element should always be. I have suppressed the J here for just to make it look compact, but you can put this small J here. Okay. What will this matrix element be? Why was this argument that A dagger A expectation value in harmonic oscillator was positive definite? The same argument will go through here. J minus on M, let it give you a new state. Then the dual vector state will correspond to J plus on the dual bra state M, right? So this has to be always greater than or equal to 0. So rewrite this explicitly in terms of your Jx plus Ijy, Jx minus Ijy. And you can write this explicitly. Can we do? Jx squared plus Jy squared can also be written as, you can add a Jz squared to it and subtract a Jz squared to it. That way, it will help us to write this state to be eigenstates of this magnetic quantum number, and I have suppressed the J, you can put the J here. Okay, you can do this. You can rewrite this Jx squared plus Jy squared as J squared minus Jz squared, and that will give us the J into J plus 1 H cross square. Okay. So please redo it again. Redo it with the J plus and J minus interchange also. That will also be positive definite, right? Please do this similar exercise for J minus J plus. This is what I was arguing for you, that J minus on M, you can put it as a ket, and then that the dual ket will be like this, and this is positive definite, and equality equal to 0 will happen when you have a state which has a lower bound. So J minus on that lower bound state is 0. This also comes automatically from here. Just like the harmonic oscillator where we took the number operator, matrix element is positive definite, you can do the same exercise without resorting to the Schwinger mechanism, Schwinger oscillator method. You can do this here. So what are the requirements? Then this being greater than or equal to 0 will put kind of a restriction here. You can simplify it. This has to be greater than or equal to 0. Equation in a neater fashion that it is greater than or equal to 0. Define a new integer k just to see that your m takes values from minus j to plus j. That we did there by a different argument, but you can go through this argument. Okay. So you find that the magnetic quantum number m has some kind of a restriction. So in fact, which is going from minus k to minus k plus h cross. And equality is applicable when j minus m is equal to 0. So you can do the same thing with the interchange j plus and j minus. Okay. Leave it to you to recheck. Tell me if I've made any typos in it. Okay. And looking at equation 3 and equation 4, you can try to find what is the common range for the magnetic quantum. And that will turn out that this common range will be from minus k to plus k. I think this H cross is not correct. It should not be. Yeah. Or you put H cross everywhere. Okay. So this is a systematic exercise where we know that J minus on minus k is 0 and J plus on plus k is 0, and we get the range of magnetic quantum number going from minus k to plus k. And then we have to do the ladder operation. This is what I was telling you in the last lecture. You can go and do it with the angular momentum algebra itself. That is what I am reproducing it for you here. So use this algebra. So this is the algebra which you would like to solve. And then if you try and solve this, you will be able to show that the J minus M is an eigenstate of Jz with M minus 1 eigenvalue. And the series of Jz should go from minus k to plus k will also tell you that you can keep doing this lowering operator. How many times? Should not go below minus k. So that will dictate for you how many times you can do this. And you can do that and get the eigenvalues of Jz. You can fix it to be mh cross, m minus 1 h cross, m minus 2 h cross, and it should terminate at minus k. You can also do the conjugate relation. This is done with Jz and J minus. You can do it with Jz and J plus. And you can go in steps of mh cross, m plus 1 h cross, and so on. So that will give you the span of Jz eigenvalues, which goes from minus k to plus k. And we have already seen that it should terminate on both sides. The J minus on minus k is 0 and J plus on plus k is 0. You can try and say that it is always, the k value could be either integral or half odd integral. These are the only two possibilities. And you can define your k, the angular momentum J by k rather than J into J plus 1 h cross. So the possible values of angular momentum will be the same. So the k, so the h cross is included in the k. So k is nh cross by 2, where n is a positive integer. And you can see that if it is odd, then it will be half odd integers. If n is even, then it will be integers. And you can fix what is j from here. J will be just in terms of this. You can fix it to be n by 2. So let's summarize. Going over only with angular momentum algebra without resorting to representation in terms of harmonic oscillator ladder operators, you can also fix what are the possible values of your angular momentum, and you can also find the eigenvalues of j squared. This we knew is j into j plus 1, and the eigenvalues of jz goes from minus jh cross to plus jh. Then comes the lowering and the raising operators. So also you can do, call this plus or minus as j plus or minus jm, and use this algebra and try and write the way we wrote C, Cn and Dn. Do the same thing here. Okay. So let's denote j plus or minus on jm as C plus or minus on jm plus or minus 1. I did it by the harmonic oscillator approach. I said you please check it out and we'll discuss it today. And this time I'm also not discussing. I'm saying this is a practice. You please work it out yourself. I'm just putting it for completeness so that you can go and look it up in case you make a mistake. So that's why I'm going very fast, since I said it's practice for you. So do this and find out what is C plus or minus mod squared. And C plus or minus will turn out from per se from angular momentum algebra also in this fashion. So I'll leave it to you here. I'll stop here.